Okay, so in the last video we basically just did a sequence, and now let me just introduce you to an idea of a series. So now basically if you had this as a sequence, basically you have this, you have to, well, basically it's easy to identify what's the difference between a sequence and a series. So a sequence basically looks something like this, and then if you have a series formed out of that sequence, then you basically have something like this. You're gonna have an initial value of 1 to infinity. So a series will just basically be a sum of that, while a sequence is just a list of numbers in order basically, and then a series will just basically be the sum of that. So that's a series. So basically, like if you are asked to evaluate a series, it's basically easy. What you have to basically do is like find the partial sum of that certain series there. So let's say you have this this type of series. So what will you do if you are asked to evaluate this? So now obviously you'll have to find like obviously this will be something like this. This will be the limit when n goes to infinity of just the summation, and now you just say I equals to 1 to n, and then basically you have this 1 over I into I plus 1. And if you check this, this will basically be a partial sum of that series. Typically we just denote it as n. So basically then you realize that this will be equals to this, and it will be equals to the limit when n goes to infinity of Sn. And basically this means that we need to identify what's Sn. So basically if you look at this thing, S1 will basically be T1, which is basically just equals to half, and S2 will just basically be half plus 1 over 6, and if you simplify that, you're just going to get 2 over 3. Then if you further continue here and you find S3, then S3 will be S2 plus T3, which basically just becomes this. And then if you further simplify, then you realize that this is equals to 3 over 4. And if you study here the pattern of what's basically happening, you realize that Sn will basically be n, because if you check here, you have 1 and 1, and if you have 2, you have 2, and if you have 3, you have 3. You can check with S4 as well. But then notice that the denominator is 1 upper than whatever the sum, the number of terms are included in that sum. Since here we're just looking for the sum of 1, here we have 2, but since here we have 2, then here we have 3, so it's 1 high, and then you basically have this. So that's basically Sn. So that technically tells you that this thing here, the summation when I goes from 1 to infinity over 1I into I plus 1, this will basically be the limit when n goes to infinity of n over n plus 1. And you can further, you can just evaluate the limit. Pretty much sure by now everybody can find the limits. Then you just divide by n, and then you have this, and basically this limit here, this one will be 0, and then you just basically have 1 over 1, which is just 1 in that case. So that's how you'll be evaluating such type of thing. With the geometric one, sequences like this, you basically know the formula for that. Even the formula for the sum to infinite terms, you have that a over 1 minus r. So these ones are a little bit hard, because you have to basically study the pattern and see what's basically happening, then identifiers, and then just take the limit afterwards. And basically in order to evaluate the sum to infinity, a series must be convergent. Likewise, we did convergent sequences, so there has to be like an idea that we have for a series to be convergent. So now let's suppose we have some sort of a series 1 over x to the p. Yeah, just x to the p, 1 over x to the p, where x goes from 1 to infinity. So let's say you basically have something like this. So when you have like this and they ask you a question, when will this series be convergent? Now there are a few things that we need to keep in mind. Basically I'm just going to tell you that something called an integral test. So with the integral test, basically what we have is that if your series is basically consists of positive terms, and it's continuous throughout, and then it's decreasing, then basically that's when you can apply the integral test. Basically with the integral test, you basically integrate this, and then basically it should just give you the value. It should give you a value. If it doesn't give you the value, then it's definitely not convergent. Okay, so maybe I can just put n here. Yeah, let's just say we have the series 1 over n to the p, so, the sum of that, basically from 1 to infinity. Okay, so now remember the conditions. Since here n is equals to 1, it basically goes from 1. If you check this, you have 1 over 1 to the p, which is just going to be 1. And then you're going to plug in 2, which you have 1 over 2 to the p. And then you're going to have, it's basically going to continue like this, basically. So you realize that obviously these things are going to be positive, all of them, because you can't raise an exponential, you can't raise a positive number to something and then it produces a negative number. So it's always positive. And remember, it should match the condition that this thing should be decreasing, and then the integral of that should basically produce a real number for it to be convergent, right? Okay, so then if you look at the integral, changing this to be in a function of x to the p, let's just say minus p, because it's 1 over x to the p, and then it's just to the power of minus p. Take that integral from 1 to infinity dx. And then basically like okay, so let's first, in order to check that this thing is decreasing, for what values of p will this thing be decreasing? It will basically be decreasing if, we'll get back to that. First, let's just evaluate this integral right here. It's just going to be 1 over minus p plus 1 multiplied by x to the power minus p plus 1. Take that from 1 to infinity. So if you do that, then you realize this, basically just going to plug 1 there and basically just have 1 over, at infinity right there, right? So if we evaluate this thing at infinity, where x goes to infinity, that's where we have to just be cautious about that. Because now, if you have like a positive number and you raise it to a negative exponent, it basically decreases. The larger the number, then the smaller that value technically becomes. For example, if you have 2 raised to minus 1, that's half. But if you have 10 to the minus 1, that's just going to be 0.1. This is 0.5. Notice that if this value tends to increase and increase, but as long as we have a negative exponent, that value will technically approach 0. So now, in order for this to produce a real number, so this thing must be negative. So that technically means that minus p plus 1 should be less than 0, because we want it to produce a real value, right? So then, if you further like solve this inequality, then you end up with something like this. P minus 1 will be greater than 0. If you multiply with a negative, then you basically change the inequality sign. And then you realize that p here will be greater than 1. So whenever, this basically means that whenever you have a p-series, we basically call these things p-series. So whenever you have a p-series and you find that the value of p is greater than 1, that basically means that that thing will technically be convergent. So you can just say it's a convergent p-series. So you can just say it's a convergent p-series, right? Okay, so then what about the cases where p is less than 1? So if p is less than 1, that will technically mean it's divergent, because now the integral will technically produce infinite, or minus, technically infinite. So, and then something basically happens. What if p is equals to 1? Notice that here, we already see a case that p cannot be equals to 1, because if p is 1, then you basically have minus 1 plus 1 and you end up dividing by 0. But nothing special really changes out of that. If p is 1, this is just the math. But if we come to the series, is it convergent or divergent? If you look here, the convergence is if p is greater than 1. But if p is equals to 1, 1 is not greater than 1. Obviously, 1 is just 1 itself. It doesn't match this condition. So obviously, it's going to be divergent. And it's a special type of a series, this one. We call it a harmonic series. It's basically going to be a harmonic series. And it's divergent. So you're going to use this type of things to work on more complicated series. So, but basically, for the integral test, what you basically need to do is to show that there's no discontinuity in your series. So your series must be continuous, and then it should be decreasing. So it should be continuous, decreasing, and positive. So that basically just are the conditions that should be met in order to apply the integral test. And basically, you should be able to show that that function is basically continuous and decreasing. But how do we show if a series is basically decreasing? You can just use derivatives. Showing that a series is decreasing, maybe let's suppose that you have this. Let's say 1 over 2 to the n. This is basically geometric, we know that. Let's say n goes from 1 to infinity. So basically, if you look at an here, an is basically 1 over 2 to the n, right? And then what basically happens is that if you change this thing to be a function of x and just say f of x, that will basically be 1 over 2 to the x. And if you take the derivative of that, that means that you're basically going to have minus 2 to the x ln 2 divided by 2 to the x squared. That's how you derive. So notice that this will cancel the square, and then you're just going to have minus ln 2 over 2 to the x, which is basically less than 0 for all x. Since here x basically will start from 1, so but this will basically be less than 0 for all x in general. So yeah, you can just say for all x values, or you can just limit them to the series, the startup value for the series. So then you show that the series, therefore this thing, therefore we can say an is decreasing. So this is how you basically do the stuff. So, and also we know that 2 to the n is positive, and therefore 1 over 2 to the n will definitely be positive, and it's definitely continuous since 2 to the n can never be 0. Then you can just do your integral test to show that this is indeed convergent. Alright, thanks for watching. Don't forget to share and subscribe.